So yesterday we have seen the graph representing the performance of the pump, and today we will use it for a better understanding how to increase the cutting performance. And for doing so, we can consider this equation that is saying something that we already know for other processes in general. Because you see that the amount of material we are removing, Qmat is the MRR that we have seen also in other processes. It is a matter of calculating the power that we have at our disposal. It can be the power of the pure water jet or the abrasive water jet. And we divided it by the specific energy that we need for removing a certain material. And you see that specific energy is expressed in joule over cubic meters. So it is the energy needed for removing a certain volume. If you do the calculations, you see that we simplify the joules, and then we have the seconds at the denominator, because the second is inside the power, and we will have a volume at the numerator. So this is the MRR. If you think about this equation, it is absolutely equal to something that we have already seen in chip removal processes, where EC is exactly the same as another quantity that was representative of that process, which is a KC. If you think about KC, it is exactly the same. And in fact, this equation is really helpful because it can allow us to compare processes. We could do the same even for forming processes, where, if you remember that theory, we have a U, which is the amount of energy we need for deforming a certain amount of material. Yeah, now I cannot write, but if you remember the stress strain curve, also considering the plastic field, where you arrive at a certain epsilon, if you calculate the area under that curve is a specific energy. So it is an energy per unit of volume, which is, again, comparable to this one. So we can compare processes. If we do it, we understand how Kc for chip removal processes is really high respect to other processes. Probably water jet is somewhere there close to the chip removal processes, because at the end, also water jet is removing a chip. Instead, if we compare with forming is much lower. So the energy that we have to put for forming is closer to the minimum value that is required by the material to be deformed. Instead, in chip removal process, we are introducing some side effects, many side effects, for example, the increase of temperature that is not strictly needed for cutting, but this is the only way for removing the chip. I already said at that time that we should minimize milling, but we know that milling is fundamental for getting the tight tolerances. So there is a space most of the time in a process chain for milling. And there you see the two formulas we have seen for the kinetic power, both in the case of pure water jet, the first one, and in the case of abrasive water jet. As I told you, we are not calculating in details the abrasive water jet power. We say just that it is proportional to the squared value of the diameter of the orifice and the power of 1.5 for the pressure. And now, yeah, just a consideration. This is taken from a scientific paper where they took a preliminary value of the specific energy from the melting energy. So they made the assumption that the same energy that you put there for melting the material is the same used for removing the material. It is an assumption which is not far from reality. This is, in my opinion, interesting. Now, this is a cutting curve, a general cutting curve. We see that it is larger at the top and it is narrower at the bottom. This is typical because we know that the jet loses energy when it's digging into the depth. And for this reason, it is able to remove more material at the top. And we see also the vector representing the feed rate. We see that it is entering into the board, which means that the jet is going in that direction, perpendicular to the board. And in order to deal with the cutting capability, we make some assumptions now. Because the first one is that we will use all the energy of the jet for cutting into the depth. For this reason, we say that in that representation, h, which is the depth, is the maximum one. In other words, it is like we are at the limit of the cut here. So the two sides at the bottom are almost closed, which means that I have used all the energy of my jet. This is the absolutely maximum depth I can achieve. In reality, this is an assumption because if I want to see the maximum cutting depth, I should carry out a non-passing through cut, and I should measure which is the depth at which the jet has arrived. In reality, since it is still able, in this case, to create a curve, it means that I still have a residual energy that could have been used for cutting into the depth, but we accept this assumption. And so the first calculation we do is for the MRR. So in other ways, first we have calculated the MRR in the previous slide, thinking about the energy needed for removing a portion of material. Now we see the same effect, so the same MRR calculated from the point of view of the workpiece. So if we do that, we can calculate the cross-section area of the curve, and you see here the calculation, 1/2 the width at the top plus the width at the bottom, and multiplied by the maximum depth. So with this formula, we are calculating the cross-section of the jet, and we multiply it by the feed rate. Like in milling, if you remember, there was a cut in front, and by multiplying it by the feed rate, we can obtain the MRR. Then we do another assumption in order to simplify the equations. We do it for a good purpose, because at the end we can make some interesting reasoning. What we do is considering now that the curve walls are parallel, which in reality is a contradiction, because I said that we are at the limit of the cut. At the limit of the cut, the curve walls would be never parallel, because they are convergent. Because if we are at the limit at a certain point, the jet is not able to cut anymore, and so the two sides should be close together. But we accept this assumption, so what we say is that the width at the top is equal to the width at the bottom. Moreover, we say that they are equal to the diameter of the focuser. dm is the diameter of the focusing tube, which again is an assumption. This last assumption is not so hard, in the sense that at the exit, the jet assumes obviously the diameter of the internal diameter of the focuser. Then it diverges a little bit, but we know that the standoff distance, so the distance between the tip of the focuser and the material, is so short that this divergence is not so much. So this last assumption is not absolutely hard. And then we say also another information that we will find again in the next lecture. And this is the fact that there is an optimal ratio between the diameter of the focuser and the diameter of the orifice. In order to better distribute the grains of the abrasive, if we do some experiments, we understand that the maximum performance in terms of cutting depth is achieved when the diameter of the focuser is 3 times in average respect to the diameter of the orifice. In other words, it is like the focusing tube has to give room to air and abrasive to enter into the jet. So for sure it has to be larger than the orifice in order not to clog. So these are the assumptions. So in other words, we are calculating the MRR, and we are distributing it on a parallel curve wall. So the section of the curve becomes rectangular. and the width becomes equal to the diameter of the focusing tube. So now, what we can do is putting together the two ways of calculating the MRR. So on the right, we have the source of the power, and in fact, you see that we are putting there just the effect of the parameters. So this is the well-known effect that we have already commented. So P elevated at 1.5 and D elevated at 2. Then there is the efficiency, C, and there is also K2, which is collecting all the constants. For example, density of the material, and everything is constant in this theory. So, for example, you see that we are not considering any orifice coefficient. All the things that are constant once defined at the orifice and the focuser are inside the K2. And in the first member, instead, we see the way of calculating the MRR from the point of view of the piece. And what we see is that there are interesting parameters there, because there is the diameter of the orifice, that's okay. And then we have two cutting performances, because we have the depth of the cut and the feed rate. In other words, we can use the power that we have at our disposal, that is represented in the second member, and we can use it for cutting into the depth or for cutting fast. And this is absolutely understandable. But there is also another passage that I can do, because if you look at this equation, I have the diameter of the orifice in both of the terms. So I could remove it from both of them. And there is a meaning for this. This is just not, it is not just a mathematical passage. Because if you think about the diameter of the orifice, it has a particular role. In the sense that, as I told you, you have to decide for the diameter of the orifice before cutting. And depending on what you want to cut and what you want to get on the cut. For example, if you are carrying out a high precision cutting operation, but and you are carrying out small pieces, probably you have to fix the N at a low value. So you are not free, in other words, to choose it. So once it is fixed, it makes no sense to keep it in this equation, because it is not a variable anymore. So you have to predefine it before. And so it is normal to cancel it. So I don't want to play on it anymore, because there are already constraints that are telling me to stay there. If you go exactly to the other side, which is high performance cutting in terms of power, in terms of cutting depth, in that case, we don't care about precision, but what we want is cutting fast. And yesterday we have seen that the best way is when you are on the knee of the characteristic curve of the pump. So we want to maximize the diameter of the orifice. So also there, it is not a variable anymore. You have to fix it at 0.30 or so, 33, depends on the pump. But again, it is not a variable anymore. So for this reason, I'm removing from this equation. So we see that in the first member, we just have the two cutting performance. And so this equation clarifies that if we want to improve the performance, we can play on the diameter of the orifice, because it is still there. It was at the second power. So I have removed one of the diameters of the orifice. It is still here, but let's remember what I have said. In reality, there are constraints, so I cannot play anymore. Or maybe I can, once I see this equation, I can change my mind. And if I want to, let's say, obtain a smaller cut, even if powerful, I know that if I do that and I reduce the diameter, I will reduce the cutting performance. But the diameter of the orifice, it can be considered as a constant when you arrive here. So at the end, you can play on, for sure, on the pressure. And instead, the discussions on the diameter of the orifice must be done before that. But we see that there is also another equation. Because if we make a step back, so if we go back here, we could say that we can keep the power of the pump constant. So we can imagine that the second member remains constant. And in that case, we would like to do this passage. Once we say that this block is constant, because the pump is providing that power, what I could do is taking that diameter of the orifice at the denominator. So it is worth making a reasoning on this, because there is something I haven't said clearly now, but now it is the time for discussing. Because if we accept that the power is constant, it seems that this equation is suggesting me to reduce the diameter of the orifice in order to increase the cutting performance, right? It seems that, I repeat, if this is constant, when I reduce the diameter of the orifice, I'm better concentrating somehow the power, right? And so if the denominator here becomes smaller, this ratio becomes higher, and so also the first member becomes higher. But there is a flaw in this discussion. There is something misleading. Can we really take the power of the pump constant by changing the diameter of the orifice? No. Because if I reduce the diameter of the orifice, the power will reduce. But it is not completely wrong. In order to discuss when it is valid or not, let's go back to the characteristic curve of the pump. Because this is the equation I would like to discuss. If I'm working here on the knee of the curve, in reality, let's try to do what I said. So let's make the hypothesis according to which the power is constant. And we know that the power is constant along this line, right? The red line that is passing from the knee. The red line is an hyperbolic behavior, and it comes from the fact that pressure times flow rate gives us the power. So if we keep the power constant, we just must move along the red line. Now, what happens if I change the orifice? I try to do what I said. So I reduce the diameter, and I would like to check if it is true that we are increasing the cutting performance or not. But let's look from the side of the pump. If I reduce the diameter, for example, I select, instead of the 0.30, I'm selecting the 0.20. And so I have the yellow dot. I'm moving to the left. But the line, the isopower that passes through the yellow dot is the yellow line that has a lower power. So there is no way. And I cannot go back on the red curve, because I could do it if you follow the line representing the behavior of the 0.20 orifice. But what should I do to go back to the red line, staying on the line of the 0.20 orifice? What should I do? That cannot be done in reality. How can I pass from the yellow dot to another dot on the red curve that intersects the line of the 0.20 orifice? I should come here somehow. But how can I go there? Increase the power, but in terms of parameter, what should I ask my CN? The volumetric flow, yes, but the volumetric flow is a consequence. It is not a parameter. What is the parameter I have to tell my pump to achieve? The pressure. The pressure is a parameter. Flow rate is not a parameter, because the flow rate is a consequence of the pressure and the diameter of the orifice. As usual, we want to play on the levers of our process, and the pressure is a lever, is a variable that I can decide for. But I cannot do that, because my pump is not able to achieve the pressure needed for getting back to the red power. So I have no solutions. So it is not true, if I am at the knee of the curve, that it makes sense to reduce the diameter of the orifice. we already discussed about that in the previous slide, so we already knew, but it is good to see these in the graph. But I told you that it is not completely wrong. In fact, if you look instead the green line, that happens, for example, when you don't need all the power of the pump. There are some materials, especially when you cut with pure water jet, that do not require the maximum pressure, maximum flow rate. So we are not at the need there. And if we start from the 0 position, that is on the curve of the 0.30 orifice, and we want to change the orifice, we switch and we go to the curve of the 0.20. We move horizontally because I'm not touching the pressure. I am at the same pressure. I'm just substituting the orifice. So I jump on the curve of the 0.20, but this time I can do what I couldn't do before, because now I can increase the pressure to compensate for the loss of the power. So I go back to the green line, and in this case, I have been able to keep the power constant. So it is true that in this case, after doing these two passages, the power is constant and the diameter is smaller. So in this case, this equation is working. So from all this discussion, especially if we keep the first one, the first case starting from the D, we understand that it is a value to increase the pressure, especially when I am in micro machining. Because in micro machining, I'm not using all the flow rate because our orifices are really small. So I'm using these orifices. So if I go down, I see that the flow rate is small. So I have too much flow rate. And instead, I would like to increase the pressure. So I would like to have a pump with a rectangular characteristic curve, but with a higher pressure and a lower flow rate. This could be doable, but I should ask the manufacturer of the pump to do a pump especially for me. We did it in the past in a contract for a company, and the pump manufacturer can change the size of the tubes, so it can adjust the pump, but the cost is higher. Instead, we can do another choice. We could buy a standard pump that has more flow rate, but there is a trick here. Let's see if you have an idea. What could I do if I have a lot of flow rate, but I need to use orifices that have a small diameter? So I'm not using all that flow rate. How could I use the flow rate? What is the choice I could make? Let's see if you have an idea. I don't want to increase the diameter of the orifice because I want to do high precision cutting. But there is still something I can do to increase productivity in this case. No ideas? Yeah, what do you mean with bypassing? So you are discharging that flow rate. We are throwing it away. Yes. Yeah, this is exactly what I would do. So my pump would work, for example, here in the yellow dot. And so I'm not using this portion of the flow rate, and I'm not using all the power of my pump. So for the pump, it is a good news in the sense that I'm wearing out the pump less because I'm not pushing too hard. But remember what I said about the machine tools. They have been designed to work at the maximum level. So I'm not using it at its best. But there is another way. It is not correct that we say that we are throwing away this flow rate. We are just not producing that flow rate. The pump is not pumping the maximum flow rate. It is pumping a lower flow rate. But there is a potential here. No ideas? If you are an entrepreneur that has a dairy pump that is not used at its best, you You can stay there, or you could invest more. Invest in what? In another cutting plant. You put 2 cutting plants in parallel, 2 cutting heads, and they are using more flow rate, and you are doubling the production. Not bad. On the same machine, because the machine is large enough, I put two cutting heads in parallel. They move together, obviously. They cannot be decoupled, and I do twice the parts in the same time. Now, let's see what happens when the abrasive touches the material. And we have said something when dealing with ultrasonic machining. So now we inherit everything I have already said. But I'm adding here something more. Because when the material is brittle, basically what happens is represented here. This is called erosion. And erosion is particularly effective when the angle of impact is 90 degrees. So the grain of the abrasive is coming from the top and it is hitting perpendicularly. If you think about the action of the wind against the mountains, so the wind is taking particles and it is hitting the vertical wall of a mountain, and after many years, it can dig even the rock. Here we are just accelerating this process, and we are using water instead of air. And so, in other words, if I want to remove more material on fragile target materials, it is better if I hit perpendicularly. Instead, we already know that if we want to remove more material on ductile materials, let's remember rotating ultrasonic machining, for example. If you look at this sketch, it is the same, basically the same. What we want to do is that the grain arrives there with a shallow angle of impact so that it creates a chip, as it happens in chip removal processes. And so there is this different behavior of that depends on the material to be cut. But I can add something more, because everything we have said is happening in every cutting curve. The difference will be that some materials will be better cut, for example, at the top of a cutting curve, and some other materials at the bottom. But let me clarify. So these are typical striations that are created by the jet. So in this case, we can say something more about striations, because in the other processes, we didn't try. We gave up, because what I told you is that it was really complex. It was a fluid dynamic composition, both in plasma and in laser. So, and also the striations were not so regular. Sometimes they had an S shape. Instead, in water jet, they are always like this. And so I can say something more. So at the beginning of the cut, you see, we are entering into the material. After some time, we have arrived with the tip of the focuser at the distance x1 from the beginning. And you see that the cutting curve is bended. And the reason why it is curved is the usual one. So the jet and the particles are losing energy. And so they have not the same cutting capability when they go to the bottom of the curve. So for this reason, they deflect. The deflection is not so much when we are at x1. When we go to x2, you see that the cutting front, because that curved line is a cutting front, you have to imagine the jet that is doing something like this, like it is represented here. And so the jet is exiting, but you see that the angle of exit tends to become more and more horizontal. So the jet is exiting quite horizontally there, because it is losing cutting power, and so it cannot dig anymore into the depth. But since there is a certain flow rate, that flow rate must be discharged somehow. And so it is moving like that, with that angle. At a certain point, what happens is represented here, where the jet tends to create a step. Because if you imagine to go ahead with this behavior, the tip is going ahead because my machine, as usual, doesn't know anything. The machine is going ahead. But the jet is tilting. At the beginning, it takes it horizontally, but there is a point where it is creating a step. It is doing something like this. It is digging here, and the jet is deflected. This happens when we are at the real limit of the cut. It is a non-passing through cut, and the jet is rebounded. But since, as I told you, the machine is going ahead, nothing is it's blocking the feed. When you go ahead at the beginning, the fact that we have a flow rate, look at this side, so the jet is large, is removing, in any case, the first steps. But at a certain point, we cannot remove them anymore because the tip has gone too far. And so there is a long way for the jet for arriving at the bottom. And when it arrives there, there is no power enough, and it is and it rebounds. Till when a new cycle of this type will be recreated, like it happens here. So, in other words, at the bottom of the curve, the situation is unstable, and in fact, if you cut a water jet curve, if you separate the two sides, you see that there are fluctuations at the bottom. For this reason, I don't want to arrive there. For this reason, I prefer to have a slab that has a thickness that is lower than the maximum cutting depth, so that I have the advantage that my cutting curve will have a good quality, because at the beginning, the material removal will happen at shallow angle of impact. So here, the jet is really effective in creating an almost vertical cutting curve. And in fact, if I look at the side or at the wall of a cutting curve cut by water jet, I can clearly see that at the top, I cannot see any striations. It is homogeneous. It is really similar to an EDM cutting curve, even if here the principle is completely different, and in any case I have particles that are creating some striations. But if you look at it, you cannot distinguish any striation here. I can also say something more, because I can say that ductile materials are cut very well here, because they prefer to be cut by shallow angle of impact. Instead, when I go too much into the depth, the cutting action of the jet on ductile materials, like metal, like aluminum, like steel, is not effective anymore, because in this case, the jet is arriving almost perpendicularly, because the cutting in front here has bended, and so some particles, look at, for example, at this picture, some particles on the cutting front are creating the chips at a shallow angles of impact, but there is a portion of the flow rate that is touching the bottom almost perpendicularly, but there the cutting action is not effective anymore. So this is another reason to arrive at the limit of the cut, especially on ductile materials. Instead, the fragile materials will be in any case removed at the top, even if I said that we are not maximizing the cutting performance, but even when we are cutting marble or stones or brittle materials, in any case, we are creating small chips at the top. And instead, at the bottom, it is true that we are removing more material, but again, we have no control. So the quality is really bad. So at the end, in both the cases, it is better that our slab, as I told you, is just using the cutting wear zone. This is the name that Mohamed Ashish gave to the part where there are no striations. Instead, the bottom of the curve is called as a deformation wear zone. Deformation comes from the behavior of ductile materials, because those materials are receiving the particles almost perpendicularly, and they are just deformed. We cannot remove so much material in that way on ductile materials. And there is a model that is able to predict the depth of the cutting wear zone and the depth of the deformation wear zone. But I was more interested in explaining why there is this cycle. There is also another interesting behavior of the jet at the exit. when the jet is arriving here, you know, a portion of the jet will be outside the material. So the most advanced portion of the jet will start exiting from the material, and it will create here a material removal ahead, like this. Which means that when the jet is going ahead, a lower portion of the flow rate is still working on the previous cutting front. So at the end, this partial distribution of the flow rate on two sides create this kind of wedge. So this material is not removed by the jet at the exit, because the most advanced portion of the flow rate is exiting ahead. And so there is not cutting power enough for removing that wedge. A way I have for reducing that wedge is slowing down. What I can do by programming the machine is reducing the feed rate there at the bottom. Because if I do that, the tile of the jet will become almost straight, and so I will remove also this material. If you imagine to start from this cutting front and to reduce the feed rate, it will become vertical, more vertical, and it will be able to remove also this portion of material. If I don't remove it, it means that my part will remain attached to the rest of the slab. And sometimes you can even use this phenomenon, because you can take the parts attached there, and then you remove the parts by hand. Now, let's see some relevant models that can be useful for completing the physical description of a water jet. The first one is an empirical model that is telling us what is the value of CD depending on the pressure and depending on the diameter of the orifice. It is an empirical one, so we don't have to discuss so much because it comes from experiments, but I'm using it, and I'm using the graphical representation for showing you how the CD can vary. Because if you look at the first orifice on the left, since there is this protrusion, it forces the water to detach clearly from the walls of the orifice itself. And in that case, we achieve a 0.5 CD. Obviously, CD is almost completely guided by CC. So the reason why CD is just 0.5 is because CC is 0.5. Because the other two coefficients are 0.97 for CD, we told this already, and C depends on the pressure, but we have seen yesterday that it is always bigger than 0.90. So CC is guiding the amount of flow rate that we are discharging. We see the second case, which is the usual one, when we have sharp-edged orifices, and in fact you see 0.65. And instead, the last one is the typical case of abrasive water jet orifices that are rounded, and for this reason you could even achieve a CC equal to 1. So I'm creating a jet that is large as the diameter of the orifice. Then I can also model the thrust force on the workpiece. I told you already that the water jet is delicate on the materials because it is not pushing so hard, even if the jet is really fast. But it is a matter of calculating the thrust as we do for hydraulic applications. This is not so different from something that you have seen. There is a turbine that uses exactly the same formula. Let's see if you remember. It is somewhere also, I'm not here, but on the other side, in front of the energy department. Yes, the Pelton turbine. If you remember the design of the Pelton blades, yeah, I should go outside. The Pelton blades were something like this. The jet was in the middle, and that shape was used for convincing the jet to go back. because in this case, we can double the thrust. And the thrust is a variation of the momentum. So we have twice the momentum if the jet rebounds completely, vertically. And this is for maximizing the use of the energy of the jet stream in the case of a Pelton turbine. Here it is exactly the same. So in other words, at the beginning of the cut, where the hole is non-passing through, we know that the jet will go up. And it is exactly there that we have the maximum thrust, the maximum force on our material. So we have to be careful when drilling fragile materials like glass, because at the beginning, when we are drilling, we have the maximum push, the maximum force. I mean, we need to break them. We have just one solution in that case. Which one, in your opinion? What could you do in terms of parameters in order not to break the glass when drilling with water jet? Think about the parameter. Think about something I can change. Obviously, I could change also the diameter of the orifice, because if the orifice is smaller, it is discharging less flow rate, less power, less thrust. But let's keep it constant, because I want to do a certain diameter. What is the parameter that is guiding this force? Parameter, again, is the lever. It's something that I can change. In reality, it's always the same. It is the pressure. What I do at the beginning of a cut, when the material is fragile, is reducing the pressure. I start, for example, from 200 megapascals. Then I wait a little bit for drilling, for giving the time for drilling. And as soon as the hole has been done, I can increase the pressure and I can go ahead. Because when the hole has been done, then the jet will be really delicate in creating the cutting curve. I can cut almost everything, even carbon fiber or whatever fiber, because it is really delicate, because one grain at a time will do the job. Instead, when I'm drilling, I have the push of the water, and water is not able to cut by itself. Okay, it is pushing, just pushing. And if I have a composite material, I risk to delaminate, because the water will infiltrate in the layer, especially if the carbon fiber is not good enough. You know that carbon fiber has a different quality. The bad quality is when you have voids, you have spaces between one layer and another. When it is really dense, in reality, the jet passes through. Okay, so I can do an experiment like this with the load cell. I can measure the force, and I know that the force has this behavior. Then we know all the equations, because we have the equation of the velocity of the jet, Vj, we have the equation of Q, and so we can put everything together in the equation of the force. So by putting these two equations inside the first one, I get this one, I get the force. So when I do this experiment, I can measure the force, so I enter on the first member here, and I can also measure the flow rate. So I have two equations, and this gives me the possibility to calculate two coefficients. And so this experiment is useful for experimentally determine CV and CC by a measurement of flow rate and the measurement of force. So I have two equations in two unknowns that are CV and CC, and I can solve it, because the rest can be calculated. Because if you remember, C is not determined experimentally, because we have the equations. We can calculate it. It is a compressible coefficient. I have to say that this kind of experiment is not so easy to make, because the thrust is not constant, so the measurement is not good. But theoretically, and there are some papers doing this for measuring the coefficients. We preferred to measure the coefficients by measuring the velocity of the jet, which is not easy to make, but I will show you how we did. Then there is also an interesting behavior of the jet that is used for monitoring sometimes, which is the thrust force. If you think about the focuser, it's like a rocket, because we have a stream of gas, in the case of the rocket. In this case, we have a stream of water that is pushing against the walls. And this gives a thrust force upwards. If I put a load cell there, I can monitor that thrust force and I can check if everything is correct. The reason why there is a difference between the different orifices and the different situations is because the maximum thrust, the maximum force, reaction force, is when we use pure water jets. Because instead, if I mount the mixing chamber and I switch on the abrasive, what will happen is that the abrasive will create a downwards force. So it will decrease the value of the reaction force. So this is the reason why. If I'm using abrasive, I'm staying on the lowest curve. Moreover, I can see that if I increase the pressure, obviously the reaction force increases. So when you want to monitor the process, this is a good way of doing that. Moreover, if you put a load cell here, you can see some spikes when you switch on and off. So it is an effective way of monitoring. And here we see that if we increase the flow rate, the reaction force decreases. The reason is the same I said already. If I increase the amount of abrasive, they will drag more downwards the focuser and the cutting head, and so the reaction force will decrease. And instead, here we see that if we are using a diameter of the orifice that is bigger, we have a more reaction force. It is like a rocket that has a bigger dimension, transversal dimension. Now, another consideration must be done about the capability of the jet to suck air, because this then gives the jet the possibility to entrain a more abrasive, which is important for us. We want to have the right amount of abrasive for cutting into the depth. And this is a representation of the system. It is important to understand that there is an ambient pressure outside, so environmental pressure, and instead the pressure that happens inside the mixing chamber is a vacuum pressure. For this reason, you see PV. But we are measuring absolute pressures. So I suggest you not to think about the relative pressures. I don't like negative pressures. They do not exist. So let's consider just positive pressures. So in other words, what I'm telling you is that the environmental pressure is 1 bar, for example, and PV is 0.30 bars, for example, 0.20. So this happens because the jet is able to entrain the air, so it is dragging the air, and for this reason it is creating a vacuum, okay? And I can measure that vacuum with this manometer here, and so I can measure the delta between the ambient pressure and the vacuum pressure. This delta is responsible for creating the flow, the flow of air. Here you see the typical flow meter. I don't know if you have ever seen it. It is exactly made like that. This is a cylinder. The flow of air is passing through, and here there is a cursor. There is a floating element that is pushed out by the flow rate, and you can read it. There are also some other ways for measuring it, because this is effective for taking a look by eyes, but not effective for having a good measurements. There are other ways. There are ways where you have a knot filament, and depending on how much it decreases in temperature, you can have a measure of the flow rate. So there are other ways. Or there are some fans. The fans can measure the flow rate, but there is a drawback there because they interact with the phenomenon. So they are changing a little bit the flow rate, even if their resistance is low. So there are many ways of measuring everything. So again, this way I can monitor the process. I'm telling you that we can use other two sensors. One is the vacuum pressure here that is really, really capable of detecting if the cut is good or not. And then the flow meter. Now, we have to understand what is the best configuration, because, for example, when I dimension here, this hole and the diameter of the holes, it is not, let's say, trivial to decide for the diameter. Now, I'm telling you how we can make. And first of all, what happens if I clog this passage? Let's imagine to remove the hose and put a finger there. And it is like I'm putting a cap there. So no flow rate. In your opinion, what would be the pressure here, PV? What do you think? What happens to the vacuum pressure? Does it increase? Does it decrease? It is the same if you clog the passage. Think about what I have said about the behavior of the jet. What do you think? The same, but the jet is dragging air. The jet is going on. The jet is on. Cannot be the same. Sorry? Okay, let me repeat. The jet is on. The jet is flowing. What I'm doing is clogging this passage. Maybe you haven't seen the arrow. This passage. I'm clogging the passage of the air. The air is off, closed. What happens to the vacuum pressure? But the jet is going down. What has to come from somewhere? The air? No? What you say can happen, but let me add another thing. In the focuser, I gave it for granted, but it is better that I tell you clearly. When the jet enters into the focuser, it is mixed with the abrasive, and it tends to occupy all the diameter. There is no empty space around the jet. So the jet is large as the whole of the focuser. So there is no way of air to flow up. But what you say is valid in pure water jet cutting. If you remember the shape of an orifice, there was the exit tube of the orifice. And in that case, I told you that the jet is finer than the diameter of the orifice, because I don't want to touch it. In that case, what you said is right, because the jet is going down, it is creating a vacuum, and the vacuum is attracting air from the sides. So the air is flowing up all around the jet and close to the wall of the exit tube of the orifice. And in fact, this is the reason why some droplets can go up and disturb the jet. And I will tell this in the micro application, because what we did for counteracting this phenomenon was pushing air from the top. We drilled an hole laterally in the mounting of the orifice in order to inflate air, in order to clean the wall of the orifice from droplets. And in this way, you can protect the jet that stays stable. But in the case of abrasive water jet, the jet is large as the bore of the focuser. So there is no space for the air for coming up. Okay, so what you say is physically right, but air cannot come here. So? No, the jet is powerful. It is going down. It doesn't stop. The vacuum here is not enough for stopping the jet. The jet has too much momentum. So what can be the solution? What happens to the vacuum there? I'm just testing your physical sense. Yeah. I didn't understand. There is something misleading. I would say that PV is a result. PV is not doing anything here. It is not used for anything for now, because I have clogged. So no need of attracting air. There is no air. There is no possibility for the air to enter. And so the vacuum is still there, but is it higher or lower than before? Lower pressure, yes. More vacuum, lower pressure. So in other words, if you put your finger here, you see, you feel, I did it, and it is not dangerous. You feel the jet sucking your finger, because it is creating more vacuum, lower pressure, because it is dragging away all the air, and so the pressure reduces. So this was important. Otherwise, if you don't understand, if you don't imagine this, you cannot understand this graph. This graph, I know that is at the first sight is complex, but let's see it step by step. Because it has flow rate on the x-axis and the delta of pressure, PA minus PV on the left. The first case is when I'm plugging, I'm closing the passage, so no flow rate. When I have no flow rate, PV, as we have said now, is the minimum value. In other words, it means that the delta between PA and PV is the maximum one. So I give you already the final equation, but now I prove how it works. So if you consider this equation, the first case with the red dot is a case where Q air is null, because I have clogged the passage. So there is nothing here. So the second term is doesn't exist. And in fact, when I remove it, I can put the denominator at the second member, and I see that in that case, the delta of pressure is equal to the maximum delta of pressure. So this is the maximum delta of pressure we can have, because the pressure in the chamber is the minimum one, because I have created the maximum vacuum. Okay, let's go now to the second point, the extreme end on the other side, which is when I'm removing the holes. So I'm not creating any disturbance, any restriction. So all the air can enter without any limitation. What happens in that case? What would be the pressure inside the mixing chamber if it is open? The ambient one. There are no other solutions, no restrictions, no losses of pressure. Because the delta of pressure could be created by the fact that if I put a hose, it is creating a loss. And so there should be a delta of pressure, right? Starting from the environmental pressure, if I follow the path, I would have a lower pressure inside because of the losses along the line. But if I have no line, no losses, and I have environmental pressure. So in this case, I look again at this graph, and what I get is the numerator here that goes to 0. And when it happens, I see that Q air is the maximum possible. Okay, in fact, this is the most, the point that stays on the right. Then I can tell you that I can connect these two dots. In order to prove it, you see some black dots that are experimental points. So this is true. So this equation works, in other words. So when understanding the two sides, we can say that in the middle we have all the other combinations. So if I partially clog, I would move along this way. I will create more vacuum. Okay. And then what I understand more is that if I increase the pressure of the water, okay, we go, for example, to 207 megapascals, we are simply creating more flow rate. So if I keep everything constant, but I increase the pressure, I'm moving to the right because I'm sucking more flow rate. If you remember at the beginning, yesterday, I said that when you think about the hopper on board of the cutting head, I needed to suck also some air after defining the amount of abrasive. Otherwise, the amount of abrasive flow rate would be coupled with the amount of pressure. And this is the explanation of that. Because if I increase the pressure of the water in order to be more powerful, the pressure will suck more air, and more air would mean more abrasive. But I decouple them because the upper on board of the mixing chamber first defines the flow rate by gravity. For example, there is an hole, and the amount of abrasive depends on just on the gravity, and only downstream I'm sucking that abrasive. So if I'm sucking more air, simply more air is entering, but it is not dragging more abrasive, because the abrasive has been decided by just the hole and the gravity. So this way I decouple them. Now, the last passage is to decide about the diameter of the hose. We already said that if we are clogging more, we are moving up. And this can be seen here. Let's consider these lines. As you see, again, as usual, they are portions of a square root. Because in fact, you see that here you have a pressure, and we know that the velocity depends on pressure. Like for the water, also air behaves like a fluid. And so if a pressure, the delta of pressure increases, the flow rate increases with the square root. So these are square root, okay? But we are seeing them by considering the vertical axis as an independent variable. Then what I can see is that if I increase the diameter of the hose, I'm attracting more air. So I'm moving from this hose that has a diameter of 2.5 millimeters to 3 millimeters to 3 and 8 millimeters. So in other words, if it is larger, it is creating less disturbance, less resistance to the flow of air, and so more air is entering. But I shouldn't exaggerate, because otherwise, what happens here is that the velocity of the air wouldn't be enough for pushing the grains of abrasive. There is a limit. So these studies arrive at the best configuration. Also experimentally, I can try all of them. I will work in different positions, and then I could select in the design phase. This is not something that the user usually does, but this is for the manufacturer of the cutting head. Now, let's see if I can show you these videos. Yeah, this is a transparent cutting head. We did it some years ago. And the jet is in the middle. But the focuser is an original focuser. This is my hand clogging the passage. You see, then when I'm clogging it, then there is also a zoom in. The jet is pulsing. And also, here I have clogged the passage. You see that everything seems frozen, but in the middle there is the jet. When I let the air open, you see that the air is destroying the jet, only at the surface. But this creates droplets. And look at the jet. Here I don't have abrasive. So you see that there is a time where the jet is finer. And it is when I'm clogging the passage. Since the air is not entering, it is not disturbing the jet, and the jet is straight. In this case, there is also empty space around, because the jet is smaller. But this is happening because I don't have abrasive. When the abrasive comes, it destroys the jet and it makes it larger. But if I don't have abrasive, I can pass through the focuser without touching it, because it is really coherent. And this video is also nice because you can imagine that I risk to clog the abrasive because of those droplets. Because every time I switch on and off, those droplets are going around. And since this is the inlet port of the abrasive, if I have abrasive there, the droplets will make the abrasive wet, and I risk to clog the abrasive, which is absolutely detrimental, because if I'm cutting a material that needs abrasive and I don't have it, I break it, especially if it is fragile. A fragile material cannot be cut by just water. I break it, like glass or like marble or ceramic material. I need the abrasive. So this is important. So we understood also from these videos that there was a need of controlling the air. The air is an important factor for cleaning even the mixing chamber. And about cleaning, if you look at this picture, you see the abrasive that is clogged all around the mixing chamber because of the droplets. But you will see what happens if I do a cycle by switching on and off the air. You see that when air is entering, it is destroying the jet, and this is cleaning up the cutting head. But you see that some abrasive stays there. So this creates a situation of risk for clogging. In literature, you can find the so-called breakup length. There is a standard in water jet that says that the length of the coherent jet is taken where the jet doubles its diameter. You can take some pictures, you can measure the diameter. When it gets double, you take that distance as the length of the jet. And when you use sharp orifices, this length is much higher. Now, if you remember from yesterday, I told you that when we consider the exchange of momentum, we still were in a optimal condition, so no losses. And even if we don't have losses, we know that the mixed jet is slower than the pure water jet, because the water is giving momentum to the abrasive, and because of the balance of the momentum, the velocity must decrease. But then we have also another reason for decreasing the final velocity, which is loss of energy in this passage. So we can define an efficiency of this exchange. And for defining it, I'm just dividing the final velocity of the mixed water jet, which is VABR, respect to the maximum velocity. The maximum velocity comes from the equation we have seen yesterday. So from this comparison, we see that the eta, the efficiency is this one. And we see that there are some factors that are playing a role on eta. For example, we see that the more we put abrasive, because we are increasing the loading ratio, the more we are creating disturbances and losses in terms of energy. And there is a theory that, a model that allows us to understand an important factor in the definition of the cutting head, which is the length of the focuser. Because for now, I haven't entered into this detail, so you could have imagined that the focuser should be always long. I don't know, for conventional reasons, it should have always a certain length. But in reality, that length comes exactly from the balance and for the consideration of the losses. Because if you consider the length of the focuser is let's say, is a compromise. Because on the one hand, it is better if it is longer, because the longer it is, the higher will be the exchange of momentum, because there is more time and more possibility to the water to increase the velocity of the jet. So asymptotically, they will achieve the same velocity, but only asymptotically. In theory, I would need an infinite focusing tube for giving all the momentum to the abrasive. Obviously, this is not feasible. And so what we do is deciding for the length of the focuser where we have exchanged 90% of the momentum. So by using that model and by using some experiments, if we are satisfied with an efficiency of the 90% of the transfer, let's say, of the velocity, momentum, obviously the physics says that we are transferring the momentum. The balance is a balance of momentum. But what we want to get is the velocity. of the jet. And if we stop at an efficiency in terms of velocity of 90%, we can define the length of the focuser. And we see here the parameters that are playing a role, also because of the previous equation. We see, for example, the role of the loading ratio. These numbers here are the loading ratios. If I'm increasing at equal flow rate of water, if I'm increasing the mass of the abrasive, I'm increasing the loading ratio. I'm putting more abrasive with the same amount of water, so I'm going to the right. And when I go to the right, we see that the length of the focuser should be lower. In other words, why it should be lower? Because otherwise I risk to lose more velocity because of friction. The model that stays at the base of the calculation of this efficiency is also considering the friction. And the friction is something that is happening on the walls of the focuser. The longer it is, the more energy we are losing by friction. So if I'm increasing the amount of abrasive, it is correct that the focuser is smaller. And also there is a dependence on the diameter of the particles. This is the mesh number. For example, if we take a mesh number 100, which means that the diameter of the particles is 0.13, we see that with the loading ratio of 0.12, the focuser should be 33 millimeters long. But in reality, in the commerce, you find focusers that are 3 inches long. It is in inches because the multinational company developing water jet are from the United States. So it is around 76. It is 76 and something, because you know an inch is 25.4. And so almost 3 inches, which means that the focuser is too long in reality for that case, because the model is telling me that 33 millimeters would be enough. So this means that the rest of the focuser, which is 40 or something more, is just used for increasing the efficiency from 90. If we measure, it goes up to 95. So in other words, it makes no sense to increase it more than that. You know, in the commerce, you cannot find all the measures, and this is the reason why 76 is the standard one, because it is the best compromise. But when we use a small bore in the focuser when dealing with a micro water jet, we needed a focuser with an hole of 0.2. Obviously, we couldn't use the usual length. Otherwise, with such a small jet, we would have lost all the power because of friction. In the case of small jets, you have to reduce the length, and we use a 10 millimeters focuser, so it is really small, because the bore was small. Consider also that making a hole in carbides with such a length and such a small diameter is really complex. What process would you use for making that hole in the focuser? Or combination of processes, right? EBM is the best candidate, but I would say that there is there is a traditional process that can do the job as a first step, and then EDM will come. Which is the process that can deal with carbides? Obviously, you should think about carbide in another state, not in the final state, in the pre-sintered state, because carbides become hard only when sintered. Yes, but what is the process? You said mold. I would say dye, because in that process, the name of the mold is dye. What process? No, yeah, you are talking about, let's say, something like injection molding, or, yeah, forming. But you cannot form by creating an hole. So the only solution would be, yeah, injection molding, but you should use a mandrel that is too long in the middle. It is not a good solution. Only one process can do this job among the traditional ones. How do you make bucatini? Extrusion, extrusion. You don't have to forget the old processes. They are still there, and they are the most competing ones. Because when we do a course like this, it seems that now we do everything with laser and water jet and ADM. But remember that the other ones are powerful and they are very well established. So extrusion can do that. Consider that extrusion can also make the mills with the passages for the water. And they are even tilted. So extrusion can also produce, you know, fusilli, right? Okay, you can tilt it. And so you have an hole with an helix. EDM, if you are crazy, you could do it by EDM with an electrode of that shape and you could screw it, but it would be crazy. Extrusion is much better. Then you sinter it, and in the case of the focuser, what you can do is using wire EDM. Once the hole has been done by extrusion, you can go with the wire and you can clean it. You can do a fantastic job like that. And connected to this evaluation of the efficiency, you can find some literature for measuring the velocity. In some cases, they have used some tracking particles. If you put some metallic particles together with the abrasive, you can track their passage in a coil. And so you can see here a spike when the particle is passing through a certain position of the coil, or one coil and another coil. Then this way you measure the time of flight, and since you know the distance, you can calculate the velocity. This is a way. I don't like it so much because you are disturbing the jet, because the particles are not exactly the same, but this is doable. So by making some experiments, you see here the combination of the diameter of the focuser, the length of the focuser, the pressure, the diameter of the orifice, and you see that here they use steel grids or steel spheres inside, and so this is doable like that. But as I told you, we prefer to measure the velocity of the jet like this, with some colleagues of the electronics department, Professor Norja. And so you have a laser source, you divide it into parts, and then you let them interact here. When they interact, they create fringes. And I can assure you that you can see the fringes. You can see line, black and white, let's say, because, you know, interference between two lasers that in reality are the same laser is really precise. So you have constructive interference and destructive interference. So it is like you are projecting in the space lines of light. When the particle is passing through those lines, it is reflecting the light. So if you have a photodetector, you can see that pulse. And then you can collect the signal with an oscilloscope, and it was possible to see a spike. These are the original spikes that were collected by the oscilloscope. And that spikes were happening at a certain frequency, because it was a pulsing light. So the disturbances of the jet, because here we didn't use any abrasive, the disturbances of the jet were creating a pulsing light. By measuring that pulsing light that had something to do with the distance of the fringes and the velocity of the jet, it was possible to calculate the velocity of the jet, because the distance between the fringes was calculable but by knowing the geometry of the system. And so maybe you can see there is a red dot here, which was the laser. It is possible to measure the velocity. A velocity that is particularly high, as I said, because it is, considering the losses, it is 500 meters per second. So this is the most delicate system for measuring it. We tried also to measure the velocity with particles, but the system was not capable, because you know, the abrasive particles are inside the jet, and you see that the jet is white there, it is disturbed, and it was not possible for the particles of abrasive to diffract, to diffuse. Diffuse is the right term, diffusing the light in a way that we could measure the velocity of the water and the velocity of the abrasive. Because in theory, we should have seen here two spikes, one for the velocity of the water and one for the velocity of the abrasive. But we were happy enough to measure the velocity like that. Once you have the velocity, you can calculate CV, for example. So we use this way for calculating the orifice coefficient. There are some papers from us about it. Maybe I will upload a review paper that I wrote last year with all we did in terms of water jet research in our lab. And these last slides are about the fact that when we use abrasive, you destroy it because the grains interact in the mixing chamber, and so what you have is a finer mesh if you collect the abrasive after cutting. And in fact, here you see that on the y-axis we have the percentage of passing particles. So in other words, let's imagine to have a sieve with constant grid distance, and so if the abrasive is becoming smaller, more abrasive will pass through. And this graph is telling me that before the use, I have a certain distribution along the mesh size. So this is the integral of all the grains when increasing the mesh size. But if I'm working at 138 megapascals for the water, I'm destroying a portion of those grains. And in fact, you see that more grains are passing through the sieve. And if I increase the pressure, I go ahead along this path. But also it is interesting to see that if the orifice is not aligned with the focuser, we are destroying more abrasive because the process is not smooth. And so the abrasive hit the wall of the focuser and they are destroyed instead of passing through. Last consideration, and then we completed this lecture, is about the premixed jet. We have already discussed about the fact that the premixed jet is a good idea, not to inject the abrasive, but to have it already inside the jet, because the abrasive has difficulties in penetrating inside the jet because it is too fast. And you know, when a jet is fast, it is behaving like a solid material. So it is true that it rebounds a couple of times and it will stay at the boundary, at the periphery of the jet, and it will be accelerated. But typically, the abrasive is not in the middle where the water is faster. The way of having it in the middle is putting the abrasive in the vessel, and then a portion of the flow rate is passing through the vessel and it joins again with the main stream here and it passes through an orifice. I already told you that the orifice cannot be made of sapphire or a diamond. It must be made of carbides, and it has to be larger. And moreover, the wear is really high. So typically in industry, we don't use this because it is too big. So the quality is not good. The pressure cannot be so high as for the injected jet. So in other words, it is a good idea under the energy point of view, but not practical in industry. But in cleaning or dismantling, or when you have to cut a wall in a nuclear plant, this jet is the best one. And you see some drawings that are representing, again, the type of equipment and the circuits that you should use. Yeah, I haven't cited this application, which is nice. Firefighters can use it. It is really clever because they can go there with a pickup, with a pump on board, and then there is a hose and a lance. And I have assisted to a presentation of this in Sweden because they invented this system in Sweden. There was a container with fire inside, and the firemen could touch the wall with the lance, and then they switch on the jet. The jet penetrates into the wall, it passes through the wall. Once it is inside, since it is water, it evaporates, and so it occupies all the volume, and so it is pushing out the oxygen. And you can switch off the fire really quickly with a tiny amount of water, respect to when you go with the usual system for firefighter. They use a big amount of water, and so if fire didn't destroy the house, they destroy the house with the water. And instead, this is really a good equipment, and it is a pre-mixed jet, because we don't need such a big pressure for passing a wall. This is just sufficient that they stay there for some seconds, and the jet will drill even a wall of some centimeters or tens of centimeters. Yeah, the disadvantages are already said there. Remember that one of the big ones is that the percentage of abrasive is reducing over time. So at a certain point, you have to stop operations and refill, which again is not so nice for industrial applications. Okay, perfect. So next week we will see the effect of the parameters. But consider that this presentation was the most important one because it is dealing with the physics, and now we have seen everything. Okay, thank you. Have a nice weekend.